The elements are the building blocks of everything we see and know around us. Conventionally, we are taught that the elements here on Earth were created in stars, colliding stars, exploding stars, and some other variants. Then, by gravitational forces, during the eons and sorting mechanisms, with lots of times involved, we can find these elements such as gold, uranium, iron, etc. in mines on the very edge of the surface of this Earth. Good day, everyone. This presentation will be about the structured atom model, the creation of the elements, and low-energy nuclear reactions, or LENR, or LENR for short. The presentation has the following topics. Let me move some here. So we have in a short intro, we have some recent activities that we've been doing with the structured atom model group. We are going to go into the physics of SAM, the underlying physics. I'm going to talk a little bit about the ICCF, or the International Conference for Cold Fusion. We're going to put the two together, if you will. I'll launch a hypothesis for you all, and then we will go into the LENR processes observed in nature for a moment, and to top it off with a conclusion, discussion, and a summarization. So, how were the elements created? Here in this table from Wikipedia, we see how the elements are created, such as exploding white dwarfs, over there, or exploding massive stars, merging neutron stars, Big Bang, etc. And even ourselves are coming into the picture with the human synthesis. The electric universe has a different view of functioning of stars, therefore our sun as well. The idea that stars are exploding hydrogen bombs is not reasonable and unnecessary in this paradigm. And the Sapphire project team, as we have been seeing the past 2 days, for example, is doing pioneering research on how the sun functions. Their experiments show transmutations taking place as we expected. If this is indeed the case, that elements are created not by these mechanisms, then the conventional explanation is no longer viable. And we need to look again at the issue of how the elements came into being. Armed with a structured atom model for the nucleus, we can now look at this topic better than ever before. Why? How? Well, that's what this presentation is about. Before continuing with that, I want to shortly, briefly summarize in a few slides what the SAM group has been doing lately. Last year, we've been doing the presentation for the first time at the Electric Universe Conference, where the structured atom model was presented. Last year, we also were able, and we, meaning James Sorensen and myself, have been able to launch a website, of which you see a screenshot. We put in a few things, like a structured atom model, of course, but also touch upon the EU geology very much, and even put in some upcoming events like this one. It's safe to say we attended and presented a poster at the ICCF 21 conference. The poster will be viewable at Quantock Hills, so you can look at that over there. And it's safe to say that transmutations was definitely the prevailing topic for us in the past year. So, then we were able to show the first 29 elements of the periodic table released to the public. The rest we hope will follow sometime soon. Let's see, where were we? Okay, we have created a tool that allows for everyone to see these elements on the website with a module which we call the Atomizer Viewer. And then there is a more complete version, which is called the Atomizer Builder, which allows any user to recreate the elements or any isotope for that matter. So this allows the SAM model to accurately depict any reaction product before, after, and sometimes even in between states of any nuclear reaction. Several enhancements were made as well, based on the previous mentioned. We have now the ability to show and place an inner electron, allowing us to further study the precise placement and the nature of these electrons. We added the extra neutron option, the neutron between parentheses here, the extra neutron to the nucleus, allowing us to make radioactive, or rather too heavy, isotopes. Then we implemented a color coding based on the conventional proton-neutron model, allowing us to explain radioactive decay in these terms. We made a huge improvement in the speed of the atomizer module, which essentially was some bug fixing there because the bigger ones were very slow. Now they're nicely fast. Then the module atomizer viewer even works rudimentary on your phone, on your smartphone, so you can actually see it over there. So this talk is from the perspective of the structured atom model, breaking with the current mainstream point of view, such as the Copenhagen interpretation in quantum mechanics, which deals with uncertainty and basically prevents any notion of the structure for the nucleus being possible. The structured atom model shows how we can explain subatomic structure and offer a different hypothesis regarding the creation of the elements throughout the Lenner reactions. Now, to put Sam into perspective, we made a slide here. On the left, we can see the quantum mechanics part, and basically it's sub-proton, sub-nucleon structure, so we're talking all kinds of quarks and all these other things, fundamental particles. I believe the current count is something way over 200 or so. They are very precise over here, and then in the end we end up with something what we would call the atom, of course, how the atom is functioned. But as you can see, nobody really has a clue on what this structure really is about. Then we have chemistry way over on the right, which basically does nothing but build with atoms, as we all know. So we have a burning candle, photosynthesis. In the middle, we have the nuclear physics, if you will, so building with the nucleons, building with the protons. That's where the structured atom model begins, if you will. So we start with one proton, one nucleon, and it goes all the way through chemistry, making the link that is right now not there, if you will, between quantum mechanics and chemistry. There's no real link there. There's no connection there. It doesn't flow automatically into one another. So this is exactly what we're trying to do, to make that one flow. There's no real difference in that sense between nuclear physics or chemistry. They influence each other. At the bottom, we see the current depiction that most people know and recognize as being the atom. In the center, you can always see a chaotic model with protons and neutrons, and it never makes sense. And if you actually study it, you'll see they create all kinds of weird shapes that are not even really possible. Right here is the first depiction of the structure for the nucleus as the SAM model talks about. So to recap SAM, when we look at the SAM, structured atom model, the following needs to be kept in mind. We have a duality, which we call a proton-electron pair, with the electrostatic force acting between them. This force is the causal mechanism for the principle of densest packing that creates geometrical shapes based on the platonic solids. These geometrical shapes in a specific order, sequence and number, create all the elements. So the neutron is not regarded as a fundamental particle, but a combination of the proton and the electron, because a free neutron, I should say, does decay into those two. So a duality, each other's opposites, it would seem. One is heavy, one is light, one is positive, one is negative, etc., etc. So when we look at the new neutron in a schematic drawing over here, we can see right there in the center what we call the inner electron. The dotted line around it is like the neutralized zone where the inner electron makes a connection to both protons on either side. So this represents deuterium, heavy hydrogen, if you will, heavy water. And we are left with a positive half a charge on the left side and positive half charge on the right side. But the whole nucleus, of course, is +1. And then we have the outer electron, in this case, -1, and making the whole charge 0, all based on the duality. In the model, as we have on the website, this is the way we depict it. And that's about it. Then, when we go a step further, we can see here the groupings, or nuclets, as we call them. James one day told me, we need a name for this. So he came up with it. We did some Googling and did some he found some synonyms, etc. And the term nuclet was born, so that's how we're going to call it. So this is this deuterium, the first one, the most important one. Here we see helium, 2 of those, if you will. This is lithium, the third element that we know. And the blue one here is carbon. Those 4 are the repeating main structures, if you will. And they keep repeating, as you will see a little bit later on, into the elements as they become heavier. At the bottom we see oxygen, neon, and this is potassium. Sodium, excuse me, this is sodium. What's nice to see, if you see this one, this deuterium here, these 2 greens are that thing. These 2 greens here are that thing. So you add them to it, if you will. The nucleus grows, and it grows principally with the deuterium, the new neutron. What we see here is, I think, the most important page. Everybody has heard and probably seen the periodic table. What we see here is the cycle of 8, or rather the second and the third row of the periodic table. Excuse me, of the periodic table. So when we take a look here at these groups, we see on the left side we get the groupings. So these are the rows, and these are the columns. And these columns are really important because when we start off with an element like an oxygen here, which is the oxygen group, then those elements usually are similar in properties. On the left side, we have the alkali metals, lithium, sodium, and then comes potassium, which is not here right now. But as you can see, it's a lithium, and the lithium is still here again on the right side. The left side, the greenish stuff, every time you see green or white, meaning it's neutralized. There's no more reactivity there. It doesn't do anything. Well, rather, that's where the activity is, where the charges are, or positive spots are left. The columns, so you can see the columns here, it stays lithium, if you will, only with an extra bit of nucleus. And that bit grows, but there's only one active nucleus. That's the active part. That gives the whole atom the properties it has. That means lithium is a +1, sodium is a +1, potassium still a +1. Same thing with the carbon group. Usually carbon is -4, +4. And the silicon can do the same thing, and the germanium can do the same thing, even though it has a lithium extra there. The carbon is still there, lending its properties to that particular atom. And the noble gases here, same similar thing, but all greenish. Well, the helium should be a little bit greenish, whitish. But they're all neutralized, meaning no more chemical reactivity. Let's see. So when we increase this shape and really look at a really large element over here, radon 222, we see that the nucleus shows polarity, which is very important, I believe, in an electric universe point of view. Then we have the nuclets, where the nucleus is structured from these repeating, recognizable geometric groupings. And the active nucleus, in combination with the larger structure, or the backbone as we call it, results in the properties of the elements. And each element is almost like a growth fragment of this tree over here, which made another rudimentary drawing here. So this is the true shape we have. You can see this splitting here, if you will. That's this center piece over there. And an element is like a piece of a partially grown whole tree, if you will. So silicon, I'm not sure how well you can see it, but this would be a silicon, I believe, with a neutral ending and a second carbon over there that we saw in the previous slide. So it's a partially grown tree. One more thing, we see over there some lines, which are the geometrical lines we have underlying in the whole structure, which are obfuscated by the protons right now, but they come out over there. That's a collision point, if you will, and I drew it schematically over on the bottom. This is where the elements become radioactive in the periodic table, meaning above lead, bismuth, lead, all the elements are per definition radioactive. How come? Well, the branches, if you will, start to collide over there, meaning there's a logical maximum to the atom, to the periodic table, if you will. This would explain why we have only so many elements. So this is a depiction of the first 29 elements that we have, starting with the hydrogens, the variations, if you will, loose hydrogen, normal hydrogen, a neutron, meaning a proton plus electron, which decays, which is actually should be, this is the deuterium, this is the tritium. Then we all the way to the right, we have the helium-3, which is a triangular instead of a linear position. This one decays automatically into that one in about 12 years, I think. Something to that effect. Releasing one of those inner electrons, which is exactly what happens because now we have 2 outer electrons over there. So it's important to see that this is a repeating thing all the way through, and it keeps repeating, and the element attributes are similar in the columns, explaining the periodic table, basically. So the atom, according to Sam, is based on the proton-electron duality. It is structured according to specific rules of growth and shapes. It shows that the properties of the elements are dictated. They are dictated by the structure of the nucleus. It is static in nature. Nothing rotating, nothing orbiting. There are no orbiting electrons, not even in quantum mechanics, by the way. That's only Bohr's model, and it works only in a one hydrogen thing. That's where the electron can orbit, or it might depend on which angle you look at it. It tends to resist absorption of energy, reverting to its ground state if possible, meaning any energy that the atom adopts from its environment, it will want to release it again. There is no need for a strong force. It's absolutely unneeded, unnecessary. The strong force was invented or postulated, if you will, because we couldn't explain at that time why the positive protons in the nucleus would stay together, mixed with some neutral neutrons that didn't really do anything there. So we needed a strong force to keep them together. We don't need a strong force because it's an electric force. That is the strong force. And it does not need mathematical equations to depict the nucleus, which I think is very important for understanding. So we have right now, let's see, okay, right. The presentation of the structured atom model at ICCF a couple of weeks ago in Colorado, at the Colorado State University. We presented this poster, which you can see over here and see in Quantock Hills in the large version. One of the most interesting things over here at that conference was there was a gentleman from India who was talking about cold fusion processes, about a smelter in India. It used quartz, silicon oxide, if you will, and scrap metal, iron. And then they had some carbon electrodes, big smelter, and they started burning off the oxygen from the quartz and releasing it as a CO2, leaving the silicon and the iron left as an alloy, and that alloy is what they were after. Now, this process was monitored carefully, and all the data showed a 24-ton metal alloy per day, which should have been 20 tons a day. So all the calculus, all the processes, all the measurements, it should have been 20, but they got 24. So one of the suspected nuclear reactions over there was a carbon plus an oxygen yielding in silicon. I will come back to that later on. This whole conference was filled with experimental data presentations. They dealt with hydrogen, deuterium fusion, lots of transmutations in nickel, palladium systems transmutating into copper and silver respectively. Then it was important that a structure for the nucleus is now allowed. It is allowed. A gentleman from Japan, Norman Cook, pointed out during a little special talk over there, which you see on the bottom over here. This is Mr. Norman Cook. And he pointed out in 2016, from the European, the European Physical Society, highly prestigious, they have accepted the notion that the nucleus might actually be structured. They're not really claiming it, they're not really saying it, because the Copenhagen interpretation kind of still stands, but they are proposing right now lattice models, meaning they're trying to depict, against their own idea, they're trying to depict right now an actual structure for the nucleus, and they've tried carbon and they've tried oxygen, I believe, so that's the state they're in. The interesting thing for me was, okay, I'm not that much of an heretic, one of the terms being used here, because it's now actually possible. It's allowed. It is allowed because the nucleus, if my fist were on the whole nucleus, and my thumb, top of my thumb were one proton, one nucleon, and I need to put 20 of those in, there's no more room for movement at all. So this is coming from the mainstream physics, pointing out that there is no movement in the nucleus at all. It must be static, it must be structured. One of the things that we learned is that there are a few things that prevent a real breakthrough in bringing Leonard to the world. There's a lack of controllability, meaning the control of the electrodes proves very difficult. They were not able to make them do the things they needed to do every time. So sometimes they got a palladium electrode, works lovely. The next time they used a palladium electrode or made a new one, it didn't work. They have a lot of trouble of making sure that they do exactly what they do. Hence, repeatability was not always assured, which is a problem. And the big conclusion was there is no theoretical model that explains all this, meaning the reactions, all the reactions we are talking about, are not understood. Even the current normal fission, which we use in everyday life, from nuclear power plants to atomic bombs and what else, we don't really understand what's going on there. So, the original experiment by Pons and Fleischmann in 1989 has been recreated by Melvin Miles in 1991 in such a way that it is, or should be, indisputable. Excess heat and helium-4 production from deuterium is precisely correlated, and we see this reaction at the bottom here, deuterium and another deuterium becoming a helium-4. Now, the Leonard community is in need of new physics, an accurate model for the atom that explains these reactions, which are shown to be true. And it has been proven that these transmutations are occurring. Excess energy, heat is proven. Now, the reliability of these results is poor, and therefore real-life applications are not really forthcoming, let alone investments. So all this due to the lack of theory, due to a lack of a theory. So, deuterium is a most important building block. It enables the Leonard reactions, if you will. I'm going to go back for one moment. It enables the reaction. What is the difference? The inner electron here stays over there. Let's say it's the top one, and this one is the bottom pair. There is no change of an inner electron becoming an outer electron, or an outer electron going into the nucleus becoming an inner electron. That is where any gamma ray would come off of it. So there's no change there, meaning no hard radiation, which is the essence, if you will, of the Leonard reaction called fusion. There is no hard radiation there, yet there are nuclear reactions happening. How can that be? Well, we believe that that is why. The inner electron doesn't change, meaning no hard radiation. So, we learned that these experiments are quite solid, but the breakthrough that could cause this Leonard reaction to be accepted remains elusive. And then we learned that we can make this difference, differentiate between hot and cold fusion, and that the SAM model accounts for and is able to depict these nuclear reactions, as we point out a few examples over here. We have started working together with several of these attendees from the conference to create and join a research group to focus on this theoretical part, which is so much needed. The research group will make an attempt to find a model for the atom that has predictive capabilities, most important, and addresses issues such as mass defect, binding energy, and all in all, it should lead to a better understanding of these reactions, and maybe one day even to real new physics. So, the electric aspects are not acknowledged enough in the Leonard field. And here is where the EU paradigm, I believe, that acknowledged the electric force so much as the principal driving mechanism and can shed some light on these phenomena, these Lenner reactions. Conversely, the EU community must take a good look at the Lenner community and understand we have much to learn from them as well. Because the link between these reactions, observations in nature, such as geology or cosmology, and a predictive model will show the electric nature of the universe, to be true. Just to mention a few observations here from nature, and to point some out. Louis Kervran, I believe a Frenchman, is a French scientist who goes into many at least suspected, biological transmutations of one, let's see, did I have it over there? Right, no. One of the reactions he points out is potassium into calcium. So potassium into calcium is only one proton difference, one next element. So when you get a, give me a second. So when we have a chicken which lays eggs with a calcium shell, and we stop feeding it calcium, the chicken still lays the eggs with a calcium shell. It's quite interesting. But what happens if we stop feeding it potassium as well? The calcium in the eggs, in the egg shell, is no longer there. Very strongly indicating that the potassium is transmutated into the calcium, which the chicken needs to lay their eggs. Then we have Peter Mungo-Job, who last year did a presentation at the Electric Universe, pointing out all kinds of observations from nature, whereby it very much looks like there is an instant petrification. Petrified animals, tree stumps, etc. And quite interesting, quite fascinating. Then we have James Sorensen, my partner here, who created, let me say that first, all these models that we saw comes from his creative mind, to put it into a model that we can all use. And he will be talking tomorrow, or maybe in Quantock Hills, and he will give a talk and explain geology through electric glasses, if you will. So point out many more observations and explain geology in general according to the electric universe and in specific transmutations. In these images here we see on the left, we see an oxygen. And in the center we see, The oxygen group is very peculiar. And that oxygen doesn't seem to fit this group because which is named after its own. When we examine this in closer, we can see that the sulfur has the right numbers, 2 times 16 making 32, to be a combination of 2 oxygens. Now, if we assume this actually does take place, what would that look like? So in these images here on the left, we see the oxygen, 2 times. In the center, we see a in-between state. This is speculative. It's not for sure at all. But we basically put 2 of these oxygens together. On the right, you see the same angle one, and the left, the second one. But there's an overlap between these 2 carbon nucleates, so 1 extra over there. Now, we can see that due to the densest packing principle, which I pointed out, meaning everything needs to be as small in the smallest sphere as possible, we see the 2 fusions, the 2 oxygens are going to resettle into this shape. It's not that easy to see, but one can see that this is sticking out way too much on the left side, if you will, if this is still the center. So it needs to be more balanced, right? That would create the true shape of the sulfur. Now, it's important to understand that the nucleus can resettle in the shape that it prefers, that it wants. Self-organizing systems was mentioned a little bit earlier. So we can see that the nucleus of the atom is indeed a self-organizing system, meaning if it doesn't like this state, it will decay or reorganize into a more stable, balanced geometrical structure. Now this is just a mere example of what we can learn from this model. There are many more enigmas and oddities about this periodic table, but in the structured atom model, they tend to be not that enigmatic, actually quite logic. So, to continue with this thought, now what if the creation of sulfur is indeed the result of 2 oxygens fusing together? How and where could we find this happening in nature? Could it be that the heavier elements are created in situ, on the Earth itself, through what is known as low-energy nuclear reactions, and that these processes are the cause for geological processes such as volcanoes, and explain the abundance of the elements? Now we see here depicted a black smoker on the bottom of the ocean, usually. And this is why I think this is a major clue for linear reactions, and I would like to address that in the next few slides. Okay. A conservative estimation is that the oceans contain at least 1 million volcanoes and many more vents, like the black smokers, that somehow spew out large quantities of sulfur, which really stands out, so much sulfur there. That is due to the heating coming from the mantle convection, at least in the standard model that we have. So standardly, we also have I can't pronounce the name properly, and nobody can really, I believe, so they call it the MOHO discontinuity, on average about 35 kilometers deep and about 500 meters thick, which is all across the Earth. Over here we can see what would be a hydrocycle, seawater seeping in, reaching the magma, coming out, and this is sorting and dissolving and all the elements and spewing it out from the black vents in the volcanoes. Now, despite what is an interesting observation here as well is that may or may not be relevant actually, is that the more basaltic the lava is, the more heavier elements are present, combined with a higher temperature. So meaning if we have lava coming up, magma coming up, and it is higher in temperature, you get more metals. If it's lower in temperature, you get more silicons. So here we see the mid-oceanic ridges and volcanoes distributed across the Earth. Now, despite many papers, and lots of research, logical explanations for geological phenomena remain absent. And Bruce Laybourne, who did a presentation, I believe, 2 years ago now at the EU, he deals with this topic and explains how they reflect currents running through the Earth in a specific circuitry, basically along these lines shown here. He gave a presentation on this topic and can be found on the YouTube channel from the Thunderbolts. And he also did a very recent YouTube group that comes together, talks about EU geology. It's called The Electric View. You can find that on YouTube as well, highly interesting. Going back to the hydrocycle for a moment. Oh, we had that one. Right, so we have a very crude sketch here again, depicting the Earth's crust. We see the cross-section of the, below is the mantle, if you will. This is this MOHO reaction zone, 35 kilometers deep. And we have a hydrocycle, which is depicted here as well, just as we saw in the previous picture. And this, it looks to me like a transporter belt almost, bringing the water, or the oxygen in this case, down. And then if we put in the linear reactions, we get an oxygen plus an oxygen creating a sulfur, one of the alleged linear reactions. Or carbon plus an oxygen, as I pointed out in this smelter in India, creating a silicon, for example. So is this reaction zone, this MOHO discontinuity, or whatever it's called, is that actually a reaction zone where these linear reactions are happening, creating, you know, lots of heat, gaseous elements like sulfur coming up, explaining the abundance of sulfur? Is that what's going on? Jumping to the solar wind for a moment. So when we when we zoom in, excuse me. when we zoom in what the composition of the solar wind is, we can see that despite almost all the elements having been detected, some elements are much more abundant than the others. In descending order, from highest to lowest abundance, we find hydrogen, helium, oxygen, and below that, magnesium, carbon, silicon, and iron. So the whites here, those elements that are colored white, are the real abundant elements, if you will. The green ones come next, if you will, and the red ones are more less often, if you will, less normal. So the real abundant elements is carbon, oxygen, magnesium, neon, silicon, and iron. Whereas iron should be somewhere. No iron. So from the sun to the earth, the sun has hydrogen turning into helium, carbon comes off as well, and fuses together into an oxygen. The solar wind has oxygen as the first most abundant element. The earth, I believe, collects water, the oxygen that has been created by the carbon and the helium, and it will turn RDs, the building blocks, for other fusion processes, like the ones I just said before. So it's like a big, the sun is seeding the earth, if you will, with what we call the carbon nucleates, which is very much the oxygen as well. So the sun keeps producing the first nucleates, as we saw at the beginning. They come in with the solar wind, the earth collects them, and I believe that the earth is actually transmutating those lighter elements into the heavier elements. So I asked myself, is this a connection to the geological activity, heat release of Lennard-type reactions, creating the earth's minerals by using liquid water? So to conclude, or make this conclusion, in nature, cold fusion seems to be happening everywhere, without significant gamma ray production even. They can be both endothermic and exothermic. Experiments are showing this to be the case. Lennard, Krivitsky, Cook, these are names of people that dive into these topics. The one missing factor is understanding, real understanding how these reactions work, why they work exactly, precisely how they work, which would provide, of course, predictability and controllability. Now, the SAM model can help us better understand these processes and help fill in this missing piece of the puzzle. This is not the only mechanism. There are many other mechanisms, as mainstream thinking points out, but this would be a missing piece of that puzzle. When we better understand these reactions, we could potentially create even new Lennard technologies for energy productions or the creation of certain elements and isotopes. Nature seems to be doing it everywhere all the time. And I believe the elements are created more or less in situ. So much remains uncertain. There are many questions to be answered. This is just the beginning. We're very much pioneering right now. And a breakthrough seems to be close, but it seems to be escaping us every time as well. So what we need to do, and it's been pointing out today before, we need collaboration between various stakeholders, if you will. We need the theorist, we need the experimentalist, and the naturalist, meaning the observations based on nature. So only by working together we will succeed. The Lennard field is a promising one, and one that I believe is in concert with the EU paradigm. The SAM model can be a conduit between the two. Some general recommendations. I believe we need some more collaboration. Not saying we're not doing enough, but we could do with some more. Crossing boundaries between disciplines or scientific fields. I think we need to cross those boundaries. We need to do this. We need to learn from other fields, such as the Lennard community, the EU community, etc. We need a new understanding or a paradigm shift, if you will. The new physics has been mentioned. In order to do that, we really need to change our thinking. And not only need to do it, we have to have the will to do that, which is easier said than done, actually. We need to attract more investments generally across the bank. Without this, progress will be slow at least. And attention exposure, this is what we need. And how do we reach the mainstream We become the mainstream, we conquer the mainstream, whatever, but we need to connect with them. Presentation objectives, I hope to have inspired at least the other people to explore this idea of in situ creation of the elements differently from the standard model. I hope to have shown the potential of the structured atom model in this short talk and its utility for learning, understanding, and education. And I hope I have emphasized that we really, really need a suitable physical model for the atom. And of course, I hope to have informed you all what we've been up to so far. Thank you on behalf of the team.